week. All right. Any questions about anything so far?
Bless you.
Okay, so basically, I kind of foreshadowed 1.2 and 1.4 edition last time with talking about what would happen with a very simple allylic carbocation, which you're going to get from a conjugated diene. Because after you do the first step of the conjugated diene, you're going to get an allylic carbocation that then you're going to have to write the resonance structures for, and then it's all the same: kinetic, thermodynamic, most stable intermediate, most stable product. Once you add the H plus to the system, or the Br plus if you're adding two Brs. Okay. So here's my first question. My first question would be, here is a conjugated diene. And so if you looked at the book or looked at the video, with a conjugated diene, it's easy to get the first product because you're going to add the H plus and then the Br minus. It was a second product that's brand new, and it's brand new because we have to write the resonance structure for the allylic carbocation, which we did on Monday. So, can you write the two products for this reaction? Is my question. Or could you at least add H plus and write the structure of the first of the carbocation? So let me give you a minute to do that for this molecule, and then you can tell me what you wrote. If it was BR2, but if we were adding BR2, then we would get something sort of like that. I want to add H plus. First thing I want to do is add H plus to this molecule, and what I want you to do is write the carbocation that you're going to get to begin with. So just add H plus to so you're going to get carbocation. There's not, so you could add. So this is symmetrical molecule, so it doesn't matter whether you add the H plus to the top double bond or the bottom double bond. And also make sure your arrows go in the right direction. The arrow always goes towards the positive charge. We got to break you of that habit of not doing that. Okay, do we add the H plus to a double bond? So let me label these A and B. And I'll label the bottom A and B just in case you wanted to add there. So tell me where the H plus goes. Does the H plus go on carbon A or does it go on carbon B? A is 1, B is 2. Okay, so I see 1s, I also see 2s. So let's write both of them out. So let's add the H to A with the plus charge on B, and then let's write the H on B with the plus charge on A. So these are my two possibilities, and you could do it to the bottom one as well, and you would end up with the plus charge with where the methyl group is, or the plus charge where the CH2 is. Okay. So this would be H plus adding to A. This would be H plus adding to B. Can you make a case for A? What's the case for drawing structure A?
It makes an allylic carbocation.
Okay, it makes an allylic carbocation. What's the case for B?
That's a 3 prime.
It makes a tertiary carbocation. Why did I start with this problem? Because in this case, we've got two arguments that we could have. We could say, okay, it's going to add to A to make the allylic carbocation, because once I make that allylic carbocation, what's going to happen next? I'm going to draw a resonance structure. So once I add the H plus to A, I'm going to go ahead and draw the resonance structure for A. And that's going to look like this. Okay, so I'm going to basically write the allylic carbocation resonance structure just like we did on Monday. What resonance structure can I draw for B? I can't. There's no other resonance structure for B. Okay. Now, the reason I gave you this molecule is because the true Markovnikov rule would be to add H plus to the carbon in the double bonds that has the most hydrogens, which is B. But the true spirit of the Markovnikov rule is we always add the H plus to make the most stable carbocation intermediate. So which of those two is the more stable carbocation intermediate? A or B? I know. I heard the first time, but nobody's jumping in. Nobody's jumping in to support you. How many people say A? How many say B? How many say I can't tell? So does resonance beat out a tertiary carbocation?
Isn't there, like, what if it forms a tertiary carbocation?
As a resonance structure? Oh, then these two guys are tied.
Then you got another guy.
Right. So that's going to make it. So that's the argument. If you're like, well, I don't know, a tertiary carbocation versus an allylic, secondary allylic carbocation. But the critical part in this case is I have two resonance structures, one of which is a tertiary. So in this case, this A is much more stable than B because one of its resonance structures is also tertiary. Now you could make an argument, well, what about the stability of the double bond? What I said on Monday was that our primary concern here would be the carbocation stability, whether it's primary, secondary, or tertiary. If you had two secondaries and you had one double bond that was more substituted than another, I guess that would break the tie. But the primary, secondary, tertiary carbocation stability is going to be what we look at first. So the argument is pretty clear, tertiary for B, but this has an extra resonance structure. Therefore, A is more stable. So this is the more stable intermediate. Okay, and the reason I started with this one is because the rule for adding electrophiles to dienes, to conjugated systems is that you're always going to add to the end carbon. So we could write numbers on this. We could say this is carbon 1, 2, 3, and 4. And since this molecule is symmetric, and I usually will always give you symmetric molecules, then I could number from 1, 2, 3, 4 from the bottom up. I'm going to get the same product. It gets super messy if this was a methyl group and this was an ethyl group, because then I would get 4 different products as opposed to just 2. So I usually stick with just symmetrical dienes. But the rule is you always add the electrophile to carbon 1. You always add to the end. Even in this case when it kind of violates Markovnikov's rule. And the reason for that is because really Markovnikov's rule is add the H plus to form the more stable carbocation intermediate, which in this case is the resonance stabilized one, not B. Okay. So I always start with this one because you could go either way. Because at the beginning you're like, why is he doing this? Because in the book they always said add to carbon 1, or I already probably said that in the video too. It's like, what's going on? Well, what I'm showing you is that's the rule, because you can always get a resonance stabilized carbocation which will be more stable than just a single one. Okay. So we're always going to add to 1, and then that sets up what we call the 1,2, 1,4 product. Right, so is that kind of clear? Because even though you're tempted not to do that, you always want to add the electrophile to carbon 1. Right. So B is out. So now what am I going to do for my second step in the mechanism here? I'm going to add my Br minus to that carbocation, add Br minus to this carbocation. Again, I'm using the individual resonance structures as intermediates, even though the true structure is the hybrid. That means I'm going to get the H and the CH3 with the bromine attached to carbon 2. So this is called my 1,2 product. Adding the Br minus to the tertiary carbocation, tertiary allylic carbocation, gives me my 1,4 product. So that's the way we label it, is 1,2, 1,4. Because I added the electrophile, nucleophile to carbons 1 and 2. I also added them to 1 and 4, but remember when it's 1, 4, the double bond moves between 2 and 3. That's the new product that you wouldn't necessarily have predicted if you didn't know about the allylic carbocations to begin with. Okay. Everybody okay with that? Because you're going to have plenty of, well, you're going to have some practice doing that for Monday. But here's my question now. 1, 2, is it the kinetic or thermodynamic? What's 1, 4? So take a minute. Which one is kinetic? Which one is thermodynamic? And let's see. Oh, we just have 1, 2, and 1, 4. I have an answer? So 1, 2 is what? How many people say kinetic? Thermodynamic? Okay. Because the thermodynamic product is the most stable product, and in this case, that double bond is more substituted. That makes 1, 4, but never do this. Never just go, oh, that's kinetic. That's automatically thermodynamic. Always check it. So this one, if we think it's the thermodynamic, did it come from the more stable intermediate? Yes, it came from the tertiary allylic as opposed to the secondary allylic. So this one is the thermodynamic product, and this one is the kinetic product. And on an exam, number one, I would probably ask you to do the mechanism for one of these problems like I'm asking you to do as the graded homework problems, because we need practice before the exam, which is not next Monday, but the Monday after that. But I could also give you a problem and say, write the two possible products and then circle the major product, and I might say, write the product under high temperature, long reaction times, and then in the other one, short reaction times, low temperature. So I'll ask you to write the product out and then put them in the right places. Which one's kinetic, which one's thermodynamic based on the conditions. So that's why we have to know that we have to remember what the conditions are. But here's one thing to not necessarily put in your head. In this case, the thermodynamic product was the 1,2 product. Is that always the case? No, it's going to depend on a case-by-case basis. So let me change this molecule. Let's go ahead and add a Br2 just so I can show you what that would look like. And what's the kinetic and what is the thermodynamic product of this reaction? And I'm going to show you a slightly different way to approach the mechanism, and then you can figure out which one works best for you. But because I know that I've got a 1,2 and a 1,4 product, I just have to remember the 1,4 product has to move the double bond between carbons 2 and 3. So if I wanted to, I could say carbon 1, carbon 2, carbon 3, and carbon 4. If all I want to do is write the product of the reaction, then all I have to do is write the 1,2 and 1,4 product. I need to know what am I adding, what's my electrophile, what's my nucleophile. In this case, my electrophile is Br plus, and my nucleophile is Br minus. Now, with Br plus, we usually wrote the triangular intermediate. In this case, I'm just going to treat it as a Br plus. Okay? Because you could say, how does how does it bridge from carbon 2 to carbon 4? And it doesn't. It's not that big. So, yes, it may bridge between carbons 1 and 2, but it won't bridge between like 1 and 4. So, Br on carbon 1, Br on carbon 2, that's my 1,2 product. Br on carbon 1, double bond between 2 and 3. Br on carbon 4, that's my 1,4 product. So it's a lot simpler just to write the product. If you just remember, what am I adding to carbon 1 to 1,4? But then if you want to work backwards on the mechanism for this, if you can do this, but you're like, I don't know about writing the resonance structure of the carbocation, that's okay. Because what we remember is, where did the bromine that added to carbons 2 and 4 come from? They came from a carbocation, right? So if they came from a carbocation, what led to the 1,2 product? What led to the 1,2 product is adding the bromine there, having the plus charge there on carbon 2 for carbon for the 1,4 product. That's the carbocation that led to that, so that we have our Br minus comes in, adds there, our Br minus comes in and adds here. So notice I'm kind of working backwards here, but part of my job is to give you multiple ways to look at a problem, and then it's your job to figure out which one works for you. Preferably all the time. So if you don't know, you can write 1, 2, take away the 2 and the 4 bromines, erase those and put plus charges. I now have my resonance structure. Now you got to add your arrow in to show how you would get from this resonance structure to this one. So we just have to show the arrow would go in that direction or the arrow would go in that direction. You do have to show that arrow showing how you convert one resonance structure into the other. I guess in the past the second one's been optional. I usually want the first one, this one, but probably a good idea to put that one in too. Okay. Resonance hybrid would finish this problem out. Well, actually what would finish this problem out is that. Showing the double bond actually adding to the Br. And that's the way we showed the arrow movement for adding Br2 to the double bond. Because remember, this is going to be essentially a Br plus and this is going to be a Br minus. And again, those arrows always move towards the positive charge. Why? Because the arrows represent the movement of electrons. They do not represent the movement of something else. They only represent electrons. Okay. So resonance hybrid, what would the resonance hybrid for this look like? First of all, the bromine would have to be added to carbon 1. Where do my delta positive charges go? Everywhere there was a positive charge. So in the two resonance structures, the two positive charges are there. That's where the delta positive charges go. Where do the partial bonds go? Between the delta positive charges. Is that different than what I was doing? Slightly, but again, all I'm doing is averaging bonds and averaging charges. So what I'm saying in this case is +1, 0, or +1, 0, delta plus. +1, 0, delta plus. Single, double bond, partial bond. Partial bond from a single, or from a single and double bond to average. So I'm still taking the averages, but in these systems, there's a pattern to it. And Top Hat's big on patterns, so they may actually have said that. It's not magic, it's just We're doing the same thing. So there's my resonance hybrid. So that's just another way to approach the problem. Last question then. Thermodynamic product, kinetic product. Which is which? Everybody have an answer? Okay. For the 1,2 product, is it kinetic or thermodynamic on 3? 1,2, the 1,2 product. 1, 2. I heard both answers. What does 1,2 come from? Well, first of all, my question is 1,2 the most stable product? No, because the double bond in the 1,4 product it has 4 attached groups. So did this come from the more stable intermediate? Yes, because it's a tertiary. So this is the more stable intermediate. This is the more stable product. So that makes 1,2 the kinetic product. And then, again, don't just assume that the other one is the same case, but it's the more stable product, so therefore it is the thermodynamic product. So these two problems go together. The problems where I just moved the methyl groups, because in one case, 1,2 is kinetic. In the other case, 1,2 is thermodynamic. All I did was change the molecule. So there is no general rule about 1,2 and 1,4 being kinetic or thermodynamic. They can be either. It depends on the problem, which is why you have to make sure that you've got the basics down, because I could ask you either one or both. So there's many modifications of this problem, one of which you'll be doing for Monday. But this is how we can change it. The rules are I will always ask you a symmetrical outdying. So that way there's no difference between 1 in one direction and counting 1 to 4 in the other direction. Okay. Any questions? Does that?
Are BR2 and HBr the only reagents that go in these problems?
No. So we can add anything that's an electrophile and a nucleophile. So for these kinds of problems, I could ask you to do HX. So HBr, HCl, HI. I could ask you to do BR2. I could also ask you to do H plus H2O. Because H plus H2O, the thing there is you're going to have an extra step in here. Because you're going to add the H plus, then you're going to add the entire water molecule and then lose the H plus. So that'll have an additional step of the H plus H2O. I could even, if I remember correctly, alcohols and waters do the same thing. So if I could change the water to an ROH instead of HOH, basically those two are the same kind of problem. And that is probably about it. I mean, I could say, what about BR2 and water? So that you would add a BR plus and then add the water, but this gives me enough variety to add. But again, whatever it is, I'm going to treat the electrophile, just add it to carbon 1, add it, and then add the nucleophile to 2 and 4. But when you add it to 1 and 4, make sure the double bond moves back to So 2 and 3. Any other questions? So this is the basic of 1,2,1,4 addition. How you get the kinetic product, how you get the thermodynamic product. It's all anticlimactic after Monday. Because sometimes what I do is I introduce the idea and then we talk about the energy coordinate diagram, but the energy coordinate diagram is almost identically the same, right? It's just my allylic carbocation came after I added the H+. But you always add to 1. You always add to the ends. Okay. All right, does that... All right, what else was on the chapter for today? The Diels-Alder that some of you did yesterday and some of you will do tomorrow in lab. And then Friday there'll be a little bit more discussion about Diels-Alder. I think it limited just today is number 1, what is the Diels-Alder? And number 2, what is the stereochemistry of the double bond and how does that affect it? And I'm going to probably get in, and then on Friday, there's a little bit of groups that go in, which is a little bit of hand waving because we don't quite go into that much detail. But here's the basics of a Diels-Alder reaction. So a Diels-Alder reaction involves a diene and an alkene. So my diene has carbons 1, 2, 3, and 4, and I like to write carbon 5 and 6 on my alkene. So it's a diene plus an alkene, and the alkene is sometimes called the dienophile, meaning diene loving. So the dienophile and the diene are going to react together to form a 6-membered ring. In organic chemistry, the big names, the big reactions have always been reactions where you can form carbon-carbon bonds. Prior to probably 1920, anybody who came up, well, most people who came up with a carbon-carbon bond reaction, bond-forming reaction, you learn their names. Grignard and Diels-Alder. I believe Diels and Alder were sort of independent on this, but they came up with the same thing at the same time. Otto Diels was a German chemist, and Kurt Alder was one of the first really famous American organic chemists. Organic chemistry is not an American science. It was developed primarily in Europe, probably a lot in Russia, but then again, nobody really knew what was going on in Russia at the time, right? Because they had SARS and death and everything else there. So it wasn't quite clear, but we still have Zaitsev and Markovnikov. Those names are associated with a lot of these important reactions. So the Diels-Alder reaction forms a 6-membered ring. And so what happens is that we can move the electrons around so that we can move the double bond between carbons 1 and 2. The double bond between 3 and 4 goes to form the 4-6 single bond. And then the double bond between 5 and 6 moves to form the 5-1 single bond. And they could go in opposite directions because honestly, that's not even the way the reaction kind of works. Our transition state then would look like this, where we'd have, in essence, partial double bonds throughout the diene, the partial bond being formed, two partial bonds being formed. So it's really it's going to look a little benzene-like, benzene being the 6-membered ring with alternating double bonds, and we'll get to it. It's what its true resonance hybrid would look like, but this is what it looks like. The reason I like to do 1, 2, 3, and 4, and then 5 and 6 is because I'm always going to form that 6-membered ring with the double bond between carbons 2 and 3. So the final product then is always going to be a 6-membered ring. It's always going to have 1, 2, 3, 4, and 5 and 6, and the double bond's always going to be between 2 and 3. anything I add to the diene, I'm going to add a group at a particular carbon. That's going to carry over into the final product. Anything I add to the alkene is going to carry over into the final product as well. So I like to number these things because then all I got to do is just figure out, okay, what's attached to carbon 1? What's attached to carbon 2? Okay. And so this is the basics of the reaction, and this is the basics of the reaction that we're doing this week in lab. The only difference is the alkene is different. And butadiene, this is called 1,3-butadiene. In its natural form, butadiene is a gas. It is the precursor to rubber tires. You take that and you polymerize it, and that's the basis of Goodyear and Goodrich and Firestone, all the people that originally did all of the polymer work in Akron, and the companies are still located there. So the car tires are made by butadiene, but it is a gas. So this week what we had to do was to heat the butadiene sulfone to kick off the SO2 to make the butadiene and then have it react. So we're doing the same reaction, it's just there's stuff attached to 5 and 6. Now there are some rules for the reaction. Number 1, the stereochemistry rules. The stereochemistry rule for the diene is that it must be in what is called the S-cis conformation. Now that's critical that it is a conformation. What do I mean by S? S stands for sigma. So there is free rotation in the butadiene around this carbon-carbon single bond. So this would be called S-cis. This would be called S-trans. So the reaction must be in the S-cis conformation. And the reason for that is what the reaction really looks like. The reaction really looks like this. My diene, let's see, how do I draw my diene? My diene, if I kind of try and look at it, sort of flat, those are all my unhybridized p orbitals, because they're making up this double bond and this double bond. But the way the reaction occurs is that diene then comes and sits on the alkene. So that what happens is that these two p orbitals and these two p orbitals at the ends of the 1,4 system and the 1,2, the spacing is perfect for those to come together, and for this one to overlap there, this one to overlap there, to then form the final product, which the final product would have a 6-membered ring again, but then the pi bond would be there. So if you had this in this S-trans conformation, the spacing is too far for it to add all at once. And that's the way the reaction works. It's the diene basically coming in and sitting on top of the alkene to make the 6-membered ring. So the conformation of the diene must be S-cis. Next rule is, whatever the conformation of the alkene is, it's preserved in the final product because the diene is coming in and plopping right down on the double bond. So if the double bond is cis, the product is cis. If the double bond is trans, those two groups add trans. So as another example, let's say I take my butadiene and I react it with that cis molecule. Right, that's our maleic anhydride from this week. The alkene Stereochemistry being cis, those two groups have to be cis. If they were trans, which is impossible in this case because of the ring, but if I said, well, let's react this like this with the trans. The first thing that usually happens is people are like, you can't do that. And then I'm like, well, I'm going to. What's stopping me? Well, but to try and avoid confusion by probably adding confusion, the reason that people say you can't do this reaction is because they see this and they go, trans, you can't use trans. I can't use S-trans conformation on the diene. Okay. So there's two different things two different transes we're talking about. As long as the alkene is in its cis conformation, S-cis, then the reaction will occur. And if you think about it, okay, the beauty of butadienes is you usually always have butadienes. So this is S-trans, all I got to do is swing it around and it becomes S-cis. I just apply a little heat to it. So yes, I can do this reaction, but what's going to happen is the two CN groups are going to be trans. Does it matter if the bold is on top or bottom? No. As long as there is a bold and dashed wedge, because this trans must be translated or preserved. That trans must be preserved over here into those two groups being trans. So the S-trans is different than trans. So the stereochemistry of the alkene is preserved, but the diene must be in its S-cis conformation. And that's usually just an issue of heating the molecule up and getting it to go there, because once it forms, it immediately adds. So that's the basics of the Diels-Alder to start with. Okay. Everybody kind of with me? So then we'll talk more about this on Wednesday. Sorry, today's Wednesday. On Friday. We'll talk more about this on Fridays from the standpoint of I still got a minute left, and I'm going to use 3 of those. Right? Never end on time. Always take a little extra minute. You add them all up at the end of the semester, and I have another class period. I want to point out one more thing. So we'll talk about like what groups should be here and what groups should be here. And then we'll also talk about the ring. If I make a ring out of this, then I have my third rule, which is endo versus exo. So that's why I want you to, if you watch the video, you may want to go back and watch those again. There's one last thing I want to add. And that's this. And maybe we'll lead with this on Friday. It won't be on the quiz. Everything I did with an allylic carbocation, I can translate to free radical allylics. And last semester, I think we talked about NBS because it was in the textbook versus BR2 and light. So I'll come back and talk about this on Friday, but if you think about trying to do a free radical reaction on this molecule, ultimately forming an allylic radical is going to be more stable. This is going to be a little bit more stable than a primary one. And you could end up with resonance structures on that. But the thing I want to point out here is that using bromine and light with an alkene is not allowed to do free radical halogenation. This is the place where we normally introduce the idea of NBS and why it's used. Okay. So that's in one of the videos as well, I believe, because there's SN2 reactions of the allylic system. So we'll kind of mop that up and talk about the Diels-Alder and beginning of benzenes on Friday. I did that down my desk this morning. It didn't end well. Okay, so I'll send out the quiz topics, but they will be probably writing a simple product of a Diels-Alder, and then whatever with the 1.2, 1.4, writing the products in 1.2 and 1.4 edition. So I'll send that email out today or tomorrow.
I guess